we're going to talk some more about radicals, which you guys kind of already know a fair amount about. But a few property reminders: if you're multiplying two radicals together and they have the same index, you can rewrite them as a single radical. I'm actually going to ask you to think about this a little bit more in a minute, but that can allow you to simplify things that you couldn't simplify by themselves. One that is new is if you have a root of another root, you can rewrite it as the root of your original value with an index of the original two indices multiplied together. I want you to think about that first property for a second, and when is it true? Sometimes there'll be some statement that says, hey, this is true if, and you guys just kind of ignore it and assume it's true all the time, but those actually do matter. In which case, or maybe both cases, is this statement true? Okay, let's simplify some radicals. So in order to be able to take the root of something, it has to be multiplied times itself, the same number of times that matches the index on your radical. You have a group inside this radical of three separate terms. It's not just the square root of your individual terms, it's the square root of the whole group. So you need to think about, if you factor that group, what can you turn it into? Well, you can turn it into two factors of x plus 2 being multiplied together. And since this is a square root, it's essentially asking, hey, what's being multiplied times itself, or what are their two matching factors being multiplied of? Well, you could also think of this as x plus 2 squared. Doing the square root of those two factors of x plus 2 gives you x plus 2. But the key is you have to write it as factors being multiplied, not as individual terms. Like on this one down here, it won't factor. If you try to do something like take the square root of the individual terms, you cannot do this, by the way. I'll show you why in a second. It is not going to give you the square root of x squared is x, and the square root of 9 is 3. That's not what this is equal to. So the reason you know that is because those aren't terms being multiplied. If you think about squaring x plus 3 and actually multiplying it times itself, it's not going to get you x squared plus 9. It gets you x squared plus 6x plus 9. So x plus 3 is not the square root of x squared plus 9. On C, just a nice little, hey, it's the square root of x to the 10th. So thinking about how many pairs of x's you have 5 pairs of factors of x's, so you're just going to have x to the 5th. On D, if you were to do a little multiplication, I'm not actually going to multiply 12 and 5 because otherwise it makes my factor tree big. I'd rather just leave them as 12 and 5 and then factor them individually. So 12 factors into 3 times 2 times 2 and then 5. So if you look for what factors you have that are being taken times themselves, you can bring out a 2 and a y squared, or 2 factors of y, because you can make 2 groups of y out of y to the 4th. And then that's going to leave you with, on the inside of your radical, still your 3 times 5, which is 15, and your x. Just go ahead and simplify on the outside, and you'll be good to go. If you have a fraction, you may just want to break it up into your radical of the top and bottom separately. So this one, if you do the 6th root of each of those, that's just going to give you r over x to the 3rd, because you can break x to the 18th into 3 groups of x to the 6th. And this one's your last property, where you can rewrite it as your index being the 2 original indices multiplied, and then we can bring out 1 factor of w. So those were all multiplying or dividing. Let's think about adding and subtracting radicals. Kind of like your other variables, they have to be like radicals before you can add them. Like you can do 2 square roots of x plus 3 square roots of x and get 5 square roots of x. But if one was square root x and one was square root y, you wouldn't be able to add them. None of these are like radicals, at least it doesn't look like they are, but they might be if we break them down and simplify. We just can't really tell at the moment. So let's break everything down. So my first radical, if I break down my 98, I can take the square root of 7 squared and have a 7 and also an x on the outside. 32 I can break it down so it has two factors of 4, so I can bring a 4 on the outside for my square root of 4 times 4, and then my last one's just xy. Okay, so if I go ahead and multiply 3x and 4 together, I'll get 12x on my middle term, and then they all are actually square roots of xy. The 7x and the 12x square root xy can be added together to give you 19x square root xy. And then the other one is just a 1 on the outside, no x terms, so it can't be combined. If you want to get fancy, you could factor out your common factor of xy if you wanted to. It doesn't matter. Let's multiply a couple of binomials together. So distributive property, you'll have to multiply your square root 2 times both of those, which they're both inside the radical in the first one. Second one, remember 5's on the outside, and then the 3's on the outside as well. And then you can combine your middle terms. Negative 5 plus 3 would give you negative 2 square root 2. And then the first one, you just have 2. And then 2 minus 15 is going to give you negative 13 minus 2 square root 2. All right, little reminder, you shouldn't have any denominators that contain a radical. If you do, your expression's not considered simplified. So what I need to do is multiply by however many missing factors I need so that everything inside my radical is like perfect square, or I can bring it outside. So on this first one, I need one more factor of 3, because if I had 2 of them, I could do the square root of 3 squared and get 3. And I have to multiply by square root 3 over square root 3 because that is the same thing as 1, so it doesn't change the value of my expression. So if I simplify, I'll get 4 square root 3 over 3. On my next one, same idea. I need another factor of x inside my radical in the denominator. So just make sure you keep your outside and your inside of your radicals separate. You're going to be able to take the square root of x squared and just get x. And then you have 3x times the square root of xy, and you can divide out your x's to get 1, so you just end up with 3 square root xy. On this one, it's a little bit more complicated because it's a 7th root and I'm missing a lot of factors. So I'm going to break it up into numerator and denominator separately under my 7th root. And then I need the number of factors that match my index on my radical. So like for square root, I need a 2. For cube root, I need 3 factors. So think about what you have. I have 1 factor of 2, and I have 5 factors of q. To get 7, that means I need 6 more factors of 2 and 2 more factors of q. So let's multiply by the 7th root of the factors that I need. So 7th root of 2 to the 6th, q to the 2nd, numerator and denominator. I know I could bring a p out, I'm just going to leave it till later though. So if I multiply, on top I'll have 2 to the 6th, q to the 2nd, and p to the 8th inside my 7th root. And then on bottom, well, my 1 factor of 2 gets added or multiplied times the other 6, so you have 7 of q and 2. So your 7th root is just going to be 2q. And then like I said, I have 8 factors of p, so I can take 6 of them and bring 1 out and just end up with that as my result. Having 2 terms on bottom instead of 1 makes it a little bit more complicated. So it's tempting to try just multiplying by square root 3, but if you do that, that square root 3 gets distributed to the 2 and the square root 3, and then you have a 2 square root 3 still in your denominator. So that won't work. What we're going to need to do instead is multiply by our conjugate. So quick reminder from your Algebra 2 days, the conjugate is the expression with the sign switch in between your 2 terms of your binomial. So that's going to make nice things happen. You'll see if we do it here. If you multiply your 2 times both of your terms, you get 4 minus 2 square root 3. And then denominator, 2 times 2 will give you 4. You get a negative 2 square root 3. And then if you multiply your square root 3 times each, you get a positive 2 square root 3 and a negative square root of 3 times 3, or just a negative 3. So your middle terms, because they were opposite signs, are going to subtract off to 0. That's why we use the conjugate. And then square root of our 9 is just negative 3. So in your denominator, you just end up with 1. No radicals. That's what we wanted. And then you don't even really have to write it over 1. You can just have 4 minus 2 square root 3.